Lesson 2.3, we're going to talk about the probability of independent and dependent events. Independent events are events that do not affect each other, so one probability is not going to affect the other probability. And then dependent events are events that do affect one another. So, for example, if I said you draw a red card out of the deck first, and then second, you draw another card, what's the probability that it's a heart? Then the first card you drew has affected the probability of the second card you drew because you've taken one card out of the deck. For conditional probability, if we're looking for the probability of event E, given that event F has already happened, this would be your equation. The probability of E given event F is equal to the probability of event E intersection event F divided by the probability of event F. So that's the probability of both of them happening divided by the probability of F happening first. In example 1, I started by listing the sample space for if we toss two fair coins, the different outcomes we could have. Now we're going to look for the probability that both land on heads given that at least one was a head. So there are 3 cases of which there was at least one head. And now I'm going to define the 2 events. So event 1 is that there's at least one head. And that is going to be a set of the 3 that I've highlighted. We could have had heads, heads, that has one head, heads, tails has one head, and tails, heads has one head. Then we're going to look at event 2. Event 2 is that there are 2 heads. And that set is only going to contain the heads, heads outcome. Since there are 4 equally likely outcomes in the sample space, in the event space, the probability of event 1 is 3 out of 4. There are 3 out of the original 4 outcomes. Also, if we look at the probability of event 1 and event 2, so that would be both heads happening, so that's heads and heads, then we're going to get 1/4, which is what we can see from event 2, that there's only one outcome out of the 4 that has both heads. So if we want the probability that both were heads, given at least one was a head, then that means we are going to be looking for the probability of event 2 happening, given that event 1 has already happened. So what we're going to do is set up that equation at the top where we're going to have the probability of event 2 and event 1 happening divided by the probability of event 1 happening. So the probability of the top we already know is 1/4. The probability of the bottom we see is 3/4. And then if you divide the fractions, which means you multiply by the reciprocal, you end up getting a probability of 1/3. In example 2, 2 cards are drawn from a standard deck without replacement. Find the probability that the second card is red and the first card, given that the first card is red. So what we're going to do is we can just kind of think about this naturally to begin with. So if we think about, given the first card is red, so if I take we start with 26 red over 52 total. Now, if I take away a red, then I'm also taking 1 out of the total. So the probability that the second card is red would be there's only 25 red left over 51 total cards. So that is going to be your probability. And we don't need to make it as complicated as using that equation at the top. Next rule we're going to look at is product rule of probability. So if you're looking for the intersection of 2 events happening, you can take the probability of event F times the probability of event E given that F has already happened. Or you can switch the E and the F around. So that could be the probability of E times the probability of F happening given that E has already happened. So in example 3, they're setting that up where they say there's a class of 2/5 women and 3/5 men. 25% of the women are business majors. Find the probability that a student chosen from the class at random is a female business major. So the big part about this one is you got to figure out what they're saying to you. So when they say that we want what's the probability that a student chosen from the class is a female business major, they're wanting to find the probability that the person is both female and a business major. So they are looking for the probability of B for business intersection W for woman. This is what we don't know. Then let's see what we would use to find that. So if we look at these equations up here, since I'm using B and W, I want to stick with that. So then let's find the probability that the person's a woman. So that's what they're saying here. The class is made of 2/5 women. So the probability that the person's a woman is 2/5. Then the probability, then here they say 25% of the women are business majors, meaning given that you're looking at a woman, 25% of those women are business majors. So they are saying to you the probability that it's a business major, given that it's a woman. So that would be that. 25%, move your decimal 2 places to the left because it's 25 over 100. So you get 0.25, which you could write as 1/4. If you like fractions or decimals, you also could write 2/5 as 0.4 if you prefer decimals. So then if I use my equation at the top, I'm going to have the probability of business intersection women equals the probability that it's a woman times it's the probability that it's a business major given that it's a woman. And so you're going to have 0.4 times 0.25, or you could think of this as 2/5 times 1/4, which ends up giving you 2/20, which is 1/10. So 1/10 or 0.1, whichever method you want to use. On the next one, we're going to talk about using factor trees and how that will help you solve some of these more complicated problems. So let's start with example 4. 2 cards are drawn from the standard deck consecutively without replacement. Find the probability that the first card's a heart and the second card is red using a tree diagram. So what we're going to start with is what's the probability that the first card is a heart. So there's 2 outcomes. You pull the card, it's either going to be a heart or not a heart. So we're going to make 2 branches to the tree, and I'm going to label them as heart and then not. So what's the probability that you pull a random card out of the deck and it's a heart? And you're going to see that there are 13 hearts in the total deck out of 52 total cards. So that's going to be a probability of 13 over 52. Or you can think of that as 1/4 if you reduce your fraction. So that's the probability of that branch of the tree. If we're looking for the probability that it's not a heart, then we're talking about 39 cards out of 52 do not have hearts. If you reduce that, that's 3/4. These 2 branches should add up to 1. Okay, so then from there, that's my first card. Now we're going to draw a second card. So the second card, we're looking for, it's red. Is it red? So for hearts, let's say I did draw a heart. So after I've drawn a heart, now I'm going to draw a second card, and it's either going to be red or it's going to be black. Or I could have not drawn a heart in the first card, and my second card could be red after that, or black after that. So I would fill out the whole tree, but they want the probability that it is a heart and it is red. So that means I'm going to be following this branch here. I'm going to be following that branch where it's heart and a red. So I don't really care about the bottom branches. I'm just going to focus up here. The probability that you pull a red card after you've pulled a heart, if you look at, so we've got 13 out of 52, but we're assuming we've pulled a heart, so there's one less red. So instead of there being 26 red, there's now only 25 red left. And instead of 52 total cards, there's only 51 cards left because we've pulled a card. We don't need the black, but just to talk about it, there's still 26 black cards in the deck if we pulled a heart, but there's only 51 total. So that's that probability. And those add up to 51 over 51, which adds up to 1. Now, if I want to find the probability that it was heart first and red second, so now it's time to answer the question. So probability of heart first and red second is equal to the probability of heart first times the probability of, and it'll be red given that, red second, given that hearts were first. So that would be the probability that it was a heart first, we see is 1/4, times the probability that it was red second and heart first was 25 over 51. We're just multiplying these branches up the tree. And we end up getting 25 over 204, which is 0.123 probability as a decimal. In example 5, 2 cards are drawn from a standard deck consecutively without replacement. Find the probability that the second card is red using a tree diagram. Just second card is red. So we don't know much about the first choice, but we know it could have been red or black. Which will affect the next draw. So we've got 26 out of 51 and then 26 out of 51 for red and black. From there, that the second card is red or black. So if I've already taken a red card, it's now going to be 25 out of, actually, wait, sorry, it's not 51, it's 52. Let's go back and change those. 52, 26 out of 52. I was already on to the next step. All right, so then I've got red and black. So now I've got 25 out of 51. And I've got, if I pulled a red and now I'm pulling a black, I still have 26 to choose from, but only out of 51. And then the same thing down here. If it's black and then red, I still have 26 red, but only 51 cards. And then for black, I have one less black and one less total. Now, if I want to find the probability that red is second, then I'm looking at this stem and this stem, but you have to multiply by the stems that they lead from. So the probability of this first one is 26 over 52 times 25 over 51, and we're going to add the other one, 26 over 52 times 26 over 51, and you end up getting 1/2.